All right, so today in section 4.2, we're going to talk about a particular type of probability distribution. In particular, this one is a binomial distribution. Well, a binomial distribution is based on a binomial experiment. So let's review what a binomial experiment would look like. A binomial experiment says that we're going to repeat it for a fixed number of trials, and each trial is independent of the other trials. So we have to make sure we're doing the same experiment the same way every time. There are only two possible outcomes of interest. There may be other outcomes, but there's really only two of interest for us. And the outcome is either that it's a success or that it's a failure. The probability of a success, P of S, is the same for each trial. So it has to be the same. And the random variable X counts for the number of successful trials. So there's a lot of variables going in here. N is the number of trials, P is the success, Q is the failure, and the failure we're going to find by taking 1 minus P. So if the success is 75%, then the possibility of failure is going to be 25%. Then your random variable X's are going to depend upon the number of successful trials. So, to start with, let's just identify whether the experiment is binomial or not. Number one, a certain surgical procedure has an 85% chance of success. The doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. So let's go through our list and see if we can identify it. So N would be the number of trials. In this case, that would be the number of patients. So that would be 8. P is the probability of success. The chance that we succeed is 0.85. Q then is the chance that we fail. And that's going to be 1 minus 0.85, which is 0.15. My random variables X are going to be, well, this is each successful surgery. So technically, we could have no successful surgeries. We could have 1 successful surgery. We could have 2 successful, 3 successful, 4, 5, 6, 7, and hopefully all 8 would be successful. And the chances are pretty good that most of those 8 will be successful because the probability is the same for each surgery at 85%. So this is a binomial experiment. Number 2, a jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. Now you can see pretty quickly as we get in here, there are 20 marbles total, but not all of those are red. And on top of that, when I start looking at the success, well, the probability that I get a red marble the first time is going to be 5 out of 20. But because I am not replacing that marble, the probability that I get a red marble the second time is not 5 out of 20. Now it's actually 4. I took the red marble out. I can't replace it. And I don't have a bag of 19 or 20 marbles now. I have a bag of 19 marbles. So the probabilities are different. So this is not a binomial experiment. All right, now comes some pretty ugly formulas. All right, so we still want to find the probability distribution. So remember, we're still doing a probability distribution. In order to do that, we have to find the probability of exactly that X success. Well, if you look at that formula, it contains a combination, which we've done before, last chapter, the combination P raised to the X power, so that's your probability of a success, raised to the X power, times Q, your failure, raised to the N minus X power, and then this is just the combination piece. The combination piece listed out, the formula for combination listed out. All right? So that means that if I'm going to use my calculator, and again, I do want to use my calculator, so let's see how I can actually figure out the formula. So a rotator cuff surgery has a 90% chance of success. The surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. So if I'm going to fill in my chart, then I need to know what N is equal to. There are 3 people being with the surgery, 3 patients. The chance of success for the surgery is 0.9, which means the chance for failure, the Q, is 0.1. And my X values then, well, there can be no successful surgeries. 1 of the patients can be successful, 2 can be successful, and 3 can be successful. This 2 is what the question is asking you. So if you read the question, it says, what is the probability of exactly 2 patients having success? But we're going to fill in the whole chart anyway. So if I use my formula, right, N is equal to 3. But I also need to know the X value. So when I'm going to do the combination, it's going to be a combination of 3 things taken 0 at a time. So the X value is 0. Then I'm going to multiply that by the 0.9, which is my P raised to the X power. So 0.9 raised to the 0 power times the failure, which is 0.1 raised to the 3rd power. Likewise, for the next one, I'm going to have still 3 things taken 1 at a time, because my X value is now 1, times 0.9 raised to the 1st, 0.1 raised to the 2nd power. So the formula is not terrible, especially whenever you look at the fact that the 0 here matches the 0 here. And when I add these 2 together, I get the 3. And I add these 2 together, sorry. 0 plus 3, I get this 3. So the 1's match, and 1 plus 2 is equal to the 3. So it's just very much a pattern. So to find the second one, it would be a combination of 3 things taken 2 at a time. I'm not sure what's going on with my chart. So taking 2 at a time, times 0.9, now 2, and then 2 plus 1 gives me my 3. And last, would be the combination of 3 things taken 3 at a time, and my 0.9 is now raised to the 3rd power, and 0.1 is raised to the 0 power. So again, it's just a pattern. So let's use our calculator and make sure that we know how to do this correctly on the calculator. Remember to type in 3C0 and put the 3 in first. So we're going to do 3. The C key is under the stats key. No, it's not. It's under the math key. Probability. Number 3 So 3C taken 0 at a time times, I'm not really sure what's going on in my calculator. Let me clear it all out and start again. Yes, let's clear the history. Let's try it one more time. Looks like maybe I wasn't on the front line. All right, now I got the calculator fixed. So again, to use my combination key, I have to type in the 3 first, then math, tab over to the probability, number 3 to get my combination key. We're taking 0 things at a time. Times, so parentheses, the 0.9 raised to the third, or raised to the 0 power first. All right. It's really struggling today. Not sure what's going on. The 0.1 raised to the third power. Hit enter, and I get 0.001 finally. Now, to help with all the struggles of this calculator, one of the best buttons on here, if you haven't already found it, is the back button, which is this second enter button. So if I hit second enter, that gives me the previous thing, and I can go back and I can now make my corrections. So the next one would be 3C1. When I change that 1, I have to change my success to a 1, and then my failure exponent to the 2. Then hit enter. And that's 0.027. Then hit the back button, second enter, and now I can back everything up. C32, and then the 0.19 is to the second power, and the 0.1 is going to be raised to the first power. And enter, and then I can do it again for the last number. And when I do so, I have, the first one was 0.001, the second one was 0.027, the third one was 0.243, and then the last one is 0.729. Now again, because this is still a probability distribution, all of these numbers should be between 0 and 1. Remember, this is the PLS, so that hasn't changed. And also, if I were to add all of these up, they should equal 1. So 9 and 1 is 10, 20. 2, 4, 6, 8, 10. So it's going to be a 0. And it does end up equaling 1.00 or 1. So the question asked me, what is the probability of having exactly 2 patients? So exactly 2 patients, here would be 2 patients. The probability that exactly 2 patients were successful, meaning the third patient was not, is 0.243. In this case, the best thing is the chance of all three being successful is even better at 0.729. And that's because the success of the surgery is so high. All right, so let's do another one this time. And I'm going to show you some additional buttons that you can use on your calculator that are going to be even easier to use. All right. So this example says, in a survey, U.S. adults were asked to identify which social media platforms they use, and there are the results. 6 adults who participated in the survey were randomly selected and asked if they use the social media platform Facebook. So I'm only looking at Facebook responses here. All right, constructor frequency distribution, or polynomial distribution. All right, so we have n, which is equal to, well, how many people did they survey? 6. So n is 6. How many people used Facebook? That was 0.68. My q is 1 minus 0.68, which is equal to 0.32. And my x values start at 0 and go all the way to 6. So from 0 to 6. Because it's very possible that none of the people none of the 6 that they randomly select use Facebook. Maybe not probable, but it does happen. And that's what we're going to find out, is how probable is that to happen. So this time, what we're going to use to make this easier is there is actually a binomial key on your calculator. So what you're going to look for is what's the binomial PDF, the probability distribution function. And you want to make sure you're looking for the P key. This is found in your calculator when you hit second, vars, because that key is a distribution key. So if I get to my calculator, clear this. All right, here's my vars key, right next to the key. You notice above that vars key, written in blue on this calculator, is distribution. So I'm going to hit second, vars. Now I have a whole bunch of different variable functions to choose from. So none of those say binomial PDF. Now here is some PDFs. Here's a PDF, but none of them say binomial. So you have to tab down. When you tab down, you get to number A and B. A is binomial PDF. B is binomial CDF. Make sure that you are hitting PDF. It will definitely change your answers. So hit enter. Now again, depending on how your calculator is designed, we need to know N, the number of trials. In this case, there are 6. We need to know P, what is the chance of success, and that was 0.68. You don't have to tell it Q because it knows how to calculate Q. And then I have to give it an X value. Now remember, I have 6 or 7 X values when you count 0 that I'm going to have to find. So I'll start with the 0, hit enter. Yes, I want to paste that into my problem. And again, if you have an older calculator, it's going to look like this to begin with. So it's binomial NPX. So it's binomial NPX. So when you hit binomial, PDF, you're going to hit the N value, the P value, and then the X value. So hit enter here, and it'll tell me my answer to this one. is 0.001073. So for binomial PDF here, it should be binomial 6.68 and 0. And my value there was 0.001 with a bunch more up here. So if I rounded to 3 decimal places, this would be 0.001. Now again, best thing about the calculator, now that I have this stored in here, if I hit second enter, it'll take me back. I can tab backwards now, and all I have to do is change this 0 to a 1. Everything else stays the same. Hit second enter, and I can go back and change the 1 to a 2. Hit enter. And then I need to do that for all 6 numbers, 0 and through 6, so all 7 entries in my table. So I would have 0.001, 0.014, 0.073, 0.206, 0.328, 0.279, and last 0.099. So if we interpret this now, it would tell us that out of all of the people who were surveyed, 68% of them used Facebook. So now if I randomly select 6 participants and ask them, do you use Facebook? The chances that none of them use Facebook is very, very little at 0.001 or 1/1000th. So 1 out of 1,000 times that's going to happen. The chance that all 6 do it is 0.099. So again, you probably won't have that many that when you randomly select 6 that all 6 do it. But if you look at these, 3, 4, and 5, those are your highest chances for getting that number of adults. And that should make sense to you because about 50% of them, a little more than 50%, use Facebook. So a little more than 50% would be the 4 and the 5. We also really, again, should check and make sure that the sum is equal to 1. And it does, because I checked it already. And we also should make sure that all of these values are between 0 and 1. As long as you're using your calculator carefully, that's usually the case. You usually don't have too much issue whenever you're not using, unless you're not using a calculator. But sometimes we do hit the wrong button. So again, checking is always a good thing. All right. So finding binomial probabilities. You don't always have to do the entire chart. Sometimes we need the whole chart because that's the whole distribution, but sometimes we just need part of the information. So this next problem will allow us to use our technology or use our formula and only do it for pieces of it, not the whole chart. So a survey found that 17% of the U.S. say Google News is a major source of news for them. You randomly select 4 adults and ask them if Google News is their major source. Find the probability that exactly 2 said yes. So we need to figure out our N. N in this case is 4 adults. The probability of a success is 0.17. The probability of a failure is 0.83. And in this case, X is equal to 2, because I want exactly 2 of them. So if I'm going to use my formula, I would have 4 combinations taken 2 at a time times my success, which is 0.17, raised to the second power. These two 2's match. Then my 0.83, also in this case raised to the second power, because these two have to equal 4. My 4 here. Or, if we're going to use binomial, we would have the binomial PDF, and my buttons would look like 4 for n. P is 0.17. And then the x in this case is 2. So I would pick your poison as to which one you want to use. If you want to use the formula, you can use the formula right here. Again, you're still going to use a calculator. Or if you want to use the distribution function on your calculator, whichever one you choose to use, I would just make sure that I knew how to use it correctly and that I was practicing way before the exam. So if I work this problem out, my answer equals 0.119. Again, you can verify that on your calculator. Then you're going to start seeing problems like this that says at least 2 responded yes. So that means that x is going to equal 2, x could be 3, or x could be 4. So now you're going to have to find this process for each one of these. So 4C2 of the 0.17 squared and the 0.83 squared. 4C3, 0.17 third raised to the third power, 0.83 raised to the first power. And 4C4, 0.17 cubed, or to the fourth power, times 0.83 to the 0 power. This top one we already knew was 0.119. The next value, if you do it correctly, is 0.016. And the last one is 0.00083. So that means a lot of decimal points. To get our answer to this, I have to add these 3 together. So I'm going to add these 3. And if I do that, I end up with 0.136. So the probability that at least 2 of them respond yes is only about 13% of the time. Right? Fewer than 2 of them respond, so fewer than 2 would say x is equal to 0 or x is equal to 1. If I'm doing binomial, I would have the binomial PDF of 4, 0.17, 0. And again, binomial PDF of 4, 0.17, 1. In this case, I have 0.475 and 0.389. If I add these up, I get 0.864. So the probability that fewer than 2 respond to as yes is pretty high. Which again makes sense because your success is low. All right, next example. It says, using the probability, I think I must have spelled probability wrong, distribution table regarding the rotary cuff surgery from one of the previous examples, we're going to graph this. So again, this graph should not be terribly hard. If you remember from rotary cuff from above, we found that we had up to 3 patients. 0.001 is the probability that there's only one success. 0.027 0.001 for no success. 0.027 for one success. 0.243 for 2 successes, and 0.729 for the 3. So just so you see, again, another example graph. We're still using a histogram. So I have 0, 1, 2, 3. This is your successful surgery. This is the probability. P of X is a P of X. In this case, my highest one goes up to 0.7, so 1, 2, 3, 4, 5, 6, 7, 8, 0.8, 0.6, 0.4, 0.2. Be very careful now because the beginning of this is very small. 0.001 is literally just skirting right along this tail. 0.027 is not really a whole lot more. So maybe up a little bit higher, but not a ton. 0.2 finally gets up higher to this. And then for 3 successful surgeries, we jump way up to almost 8. So this graph, does indicate that more than likely we're going to have a successful surgery. The graphs are interesting, but not always telling. It will be more when we talk about normal PDFs. So just like before, we can find the mean, the variance, and the standard deviation. This time the mean is very simple. It's just xn times p. So the number of trials times your success. Your variance is n times p times q. Standard deviation is always to take the square root of variance, so it's the square root of n times p times q. So very, very simple to find the mean, standard deviation, and variance, which is nice. So for this example, in Pittsburgh, Pennsylvania, about 56% of the days in a year are cloudy. Find the mean, variance, and standard deviation for the number of cloudy days during the month of June. Interpret the results and determine any unusual values. So we're talking about the month of June. How many days are in June? 30. So we do need to know that that's days in June. All right. P in this case is equal to 0.56. Q is going to be equal to 0.44. My mean is going to equal n times p. So my mean in this case is 30 times 0.56, which is 16.8. Mind you, that is days. Our variance is going to be n times p times q. So 30 times 0.56 times 0.44. If I multiply that out, I get 7.4. And then my standard deviation is going to be the square root of 7.4. So my standard deviation is equal to 2.7. So what does this mean? It means in the month of June, about 16.8 days will be cloudy in the month of June in Pittsburgh, Pennsylvania. So what's usual then? So this is the average. So this is the average So on average, every year, about 16.8% of the days will be cloudy. So, question also asks about unusual values. Well, if you remember unusual values says take the mean and subtract 2 times the standard deviation and add 2 times the standard, 2 plus mean plus 2 times the standard deviation. So this would be 16.8 minus 2 times 2.7, which is equal to, if you use your calculator, 11.4, or 16.8 plus 2 times 2.7, that's equal to 22.2. So again, usual rain or usual cloudiness would be between 11 and 22 days. So anything outside of this, so less than 11 or greater than 23, if you want to keep it days and days, or greater than 23, would be unusual. So less than 11.4, which would be 11 days, because remember we're rounding this to days, or greater than 22.2, so you have to round that one up. So if it had less than 11 cloudy days or greater than 23 cloudy days, then those would be unusual. Average is 17. Unusual would be less than 11, greater than 23. All right, and that wraps up this last section and also everything we're going to do in Chapter 4.